Hello everybody, welcome back to Catalysis, Discovery and Technology Tool, where we discuss and explore catalysis and its future in science and medicine. In this lesson, we will be learning the fundamentals of kinetics, so let's get right into it. This lesson includes basics of kinetics, rate laws, and non-power law kinetics. The basics of kinetics. Reaction kinetics is the study of rates of chemical reactions. So what does this have to do with enzymes and catalysis, and why do we care about reaction rates? Whether it's producing fuel for cars or treating illness, many processes involve chemical reactions. It is essential that we understand how quickly those reactions happen and how we can speed up or slow down reactions by specific amounts. Enzymes increase reaction rates, and to understand their functioning, we'll need to know how reaction rates are calculated. So what affects reaction rates? Reactions are caused by collisions of molecules. The collisions must be hard enough to rearrange bonds, but not so hard that the molecules fly past each other. Increasing the frequency of collisions increases reaction rates. This can also be done by increasing temperature and increasing the number of molecules present, and by reducing the energy needed to rearrange bonds. Enzymes function by reducing the energy needed to rearrange bonds. Rate laws. Rates are defined as rate laws. These are mathematical relations between the important properties in the reaction rate. Reaction rates are defined in various ways, but the most common is to describe how quickly the concentration of a chemical changes. Consider the following reaction and rate law. If A is our reactant and B is our product, two molecules of A react to form B. The rate of reaction with respect to A is equal to negative K times the concentration of A squared, where K is the rate constant. This says that the rate of reaction with respect to A is proportional to a rate constant of K and the concentration of A squared. Note that this concentration is usually in units of moles per liter. This type of rate law is called a power law. This is because the rate is proportional to some power of the concentration. In this case, that power is squared. So this reaction is second order in A. Rate laws must be determined experimentally. That is, there's no easy way to look at a reaction and tell what its rate law is. Experiments are usually done in some way that we can measure the rate and the concentration. Sometimes this is extremely difficult, so we will not go into detail of these experiments right now. First, we usually try to determine if a reaction is elementary. Take a look at this one for example. 2A plus 1B react to form 1C and 1D. Elementary means that the powers in the rate law are equal to the stoichiometric coefficient of the reactants. If the rate law is the rate of reaction is equal to the rate constant times the concentration of A squared times the concentration of B, then it is elementary. Any other rate law, and it means that the reaction is not elementary. Normally 1 is not shown, but it is left here to illustrate the concept. This may seem strange, but this reaction being elementary is very common in nature. Let's use some data to find out the rate law for the following reaction. 2A reacts to form B. An experiment was done and the following data was collected. We want to know, is this reaction elementary? If not, is it power law? If so, what order? We see that the rate increases as the concentration of A increases, but how can we determine the order? Let's do some math. The negative rate of reaction with respect to A is equal to the rate constant multiplied by the concentration of A to the alpha power. Essentially, we want to see what alpha is. If alpha is A, then the reaction is elementary. How can we rearrange this to make alpha easy to see? Let's linearize the equation. Linearization is a common technique that takes some practice to get used to. We'll do a few examples. The idea is to turn our unknowns into something that looks like a slope and a y-intercept from a linear equation. Our unknowns here are alpha and k. Can you think of how to do this? So if we plot the natural log of negative RA versus the natural log of CA, both of which are known, then the slope should be alpha, and the y-intercept should be the natural log of k. Let's try it out. Just take the natural log of both sets of our data from earlier. We get a line. If we measure the slope and check the y-intercept, we will see the slope equals 2 and the y-intercept equals 1.5. Fitting data like this to a line for the best possible fit is called linear regression. This topic will not be covered in these slides. Alternatively, if the data looks like a line, you can simply measure the change from any 2 points in the vertical axis, delta y, and the corresponding change in the horizontal axis, delta x. Slope equals delta y divided by delta x. In this case, let's pick the 2 farthest points. The highest point is at 1.5, 4.5, and the lowest point is at negative 1.5, negative 1.4. The y-intercept can directly be seen here to be 1.5. If your data does not include the y-intercept, you can simply solve for it using any point. So what does all of this mean? Going back to our original equations, if 2a reacts to form b, and our proposed rate law is negative RA equals kCa to the alpha power, our linearized rate law becomes the natural log of RA is equal to the natural log of k plus alpha multiplied by the natural log of negative Ca. The slope is alpha, the order of the reaction, which is equal to 2. That means that our reaction is order 2 in A. Since the coefficient in front of A is 2, that means our reaction is elementary. We also get the rate constant, K. Let's do another example. We'll look at a similar reaction. A reacts to form B. Is this elementary? That means, when we linearize our data, does the slope equal 1? Data for this reaction are provided on the next page. This looks different than before. The rate increases with the concentration of A, but looks like it doesn't increase as quickly at higher concentrations of A. Let's linearize it like we did before and see what we get. Note, these experiments are done by adding varying amounts of A to a reactor with a catalyst and measuring the immediate rate, then repeating. So each step, there is no B present. This will be important later. This does not look like a line. So what does this mean? Our reaction must not follow power law kinetics. Let's learn about some reactions that do not follow power law kinetics, like catalyzed reactions, which are almost never power law. Non-power law kinetics. When reactions follow power law kinetics, it is usually because the reactions happen in a single step. The molecules simply collide and react. There are examples where reactions appear to follow power law kinetics, but careful experiments have shown that they do not happen in a single step. Catalyzed reactions occur in many steps, so they usually do not follow power law kinetics. If we can imagine what the individual steps are that lead from reactant to product, then we can produce a rate law. Each individual step will be elementary. Sometimes, even if the steps we guess do not exactly follow what really happens, our rate law will still fit the experiments well. This is usually good enough. Let's assume this reaction, since it does not follow power law kinetics, is catalyzed. Steps for catalytic reactions typically follow the same pattern. The reactant approaches the catalyst. This is called diffusion to the catalyst. The reactant attaches to the catalyst. This is called adsorption. The reaction reacts to become products. This step can have many forms depending on the nature of the reaction. Is there only one reactant? If there are two reactants, does the other reactant need to absorb too? The products detach from the catalyst. This is called desorption. The products leave the catalyst. This is called diffusion away from the catalyst. Typically, steps 1 and 5 happen quickly. We say they are not rate limiting and thus can be ignored. This describes the process for heterogeneous catalysts. This means that the catalyst is a separate phase from the reactants. The catalyst is usually solid for a heterogeneous catalyst. So what do these all look like? Diffusion to the catalyst. Adsorption. Reaction. Desorption. And diffusion from the catalyst. So how does this affect the rate? Let's look at each step individually, but we'll ignore diffusion to and from the catalyst for now. Remember, our overall reaction is A forms to make B. Each individual step will be elementary. The rate is proportional to the concentration of A and the concentration of free spots on the catalyst, called sites. But what can also happen is A can desorb without reacting. This can be represented by the reverse reaction. A times S reacts to form A and S. Thus, the rate of the reverse reaction is equal to K negative ADS multiplied by the concentration of AS. Rather than write this as two separate reactions, we say this reaction is reversible. The net rate of absorption is then the sum of the two rates. Sometimes we factor out K-ADS and define Ka equals K-ADS over K negative ADS. This number represents the affinity of A for the catalyst. If Ka is high, then A will absorb more than it desorbs. Reaction. The rate is proportional to the concentration of AS that is absorbed onto the catalyst. We'll assume the reaction is not reversible, but sometimes it is. Desorption. Desorption is also reversible. Here, Kb is defined the same way as Ka. It represents the affinity of B for the catalyst. Summarizing. Adding up the three steps, all of the intermediates cancel out and we're left with the overall reaction. So how do we get a rate law from this? There's quite a bit of algebra that happens, but the important facts are we cannot have in our rate law the concentration of free sites or occupied sites. This is because that is impossible to measure. Our rate law should only include concentrations of our reactants and products. While we can't know the number of A-bound sites, B-bound sites, or free sites, we can know the total number of sites. One of the steps will be rate limiting. This means that the overall rate will equal the rate limiting step. It could only be one of the three, but typically the reaction is rate limiting. So why does the overall rate equal the limiting rate? Think about driving to work or school. Let's say there are 3 parts to the trip, and each take about 5 minutes normally. Leave your neighborhood road, take a highway to town, and ride through town to your school. If there is a wreck in town and it adds an hour to your trip takes about an hour. It doesn't matter if you speed on the highway or in your neighborhood, you will be taking about an hour to get to your destination. With reactions, the rates we're looking at vary by tens to 10,000s of times. Imagine if the traffic jam in town added 5 days to your trip. Speeding on the highway would save you essentially no time. Your speed is limited to the lowest speed on your journey. The steps that are not limiting will have a net rate of 0. The forward and reverse happen so much more quickly than the limiting step that they are at equilibrium. This assumption is known as the pseudo-steady state hypothesis. It is usually a very good assumption. We then write out our rate limiting step to see which unknowns we need to remove. We then use a catalyst balance to eliminate our unknown, CS, and substitute back into our limiting step. So we have our rate law. The next question is, does this fit our data? This rate law is quite different from power law rate laws. This is dependent on the concentration of B. Any constants that are multiplied together can be lumped together. How do we see if this fits our data? The best way is to linearize it again. We want to rearrange our rate law so that it looks like it is a line. That is, some rearranged rate of reaction plotted against rearranged concentration of A, which looks like a line. Again, this takes some practice. To linearize this equation, we flip both sides. This may not look like a line, but remember that for this experiment, the concentration of B equals 0. Now we can plot 1 over the rate of reaction versus 1 over the concentration of A. The slope should be 1 over K prime, and the y-intercept will be Ka over K prime. It fits. This means that our proposed mechanism is probably correct. By doing regression, we can get numerical values for the slope and intercept. In this case, the slope is 0.1 and the y-intercept is 0.2. Note that we'll have to do experiments with B in them to get Kb, but the process will be the same. Note that at high values of Ca, the rate does not increase as quickly. This is because there is relatively little unoccupied catalyst left. The catalyst has become saturated with reactant. Essentially, the reactants are waiting in to get access to the catalyst. So what other types of rate laws are there? The name of the form of kinetics we just derived is langmuir-Hinshelwood, which is an extremely common form. Things that can change with this type of analysis for heterogeneous catalysis are Adsorption or deabsorption could be limiting. Diffusion could also be limiting. There could be more than one reactant and/or product. Not all reactants or products may absorb to the catalyst. Some reactants or products may need multiple catalyst sites to absorb, and the reaction may be reversible. There could be multiple reactions. What if diffusion is limiting? This is frequently the case for reactions, which must happen at high pressure. Since heterogeneous catalysts are often active at the surface, catalysts are often made to have extremely high surface area. Heterogeneous catalysts are often thin coatings on high surface area supports. Think of a fine mesh or gauze. These supports must be stable and non-reactive. There is a trade-off between surface area of catalyst and pressure drop across the reactor. If a support is made to have too high of a surface area, then the reactants are forced to pass through very small pores, increasing the pressure drop. If a support is made to have too low of a surface area, then excess amounts of catalysts are needed. How can we tell if diffusion is limiting? There are two types of diffusion: external diffusion to the catalyst from the bulk material, and internal diffusion that occurs within the catalyst particles. To determine if a reaction is limited by external diffusion, there is a very simple test. The method is by stirring or agitating the reactants. Stirring increases diffusion by increasing convection. If the reaction is externally diffusion limited, the rate will increase while stirring. If the reaction is limited by anything else, stirring will not increase the overall rate. To determine if a reaction is limited by internal diffusion, the easiest method is to decrease the catalyst particle size. This will decrease the total distance reactants have to do to diffuse. If the reaction is internally diffusion limited, the rate will increase with smaller catalyst size. If the reaction is limited by anything else, decreasing particle size will not increase the overall rate. To summarize the steps in determining a rate law, you first collect experimental data, which was not discussed here. Second, you propose a mechanism. Third, assume a step is limiting, usually the reaction. All other steps are at equilibrium, so the net rate for those reactions is 0. Fourth, you solve for unmeasurable quantities. Fifth, you substitute unmeasurable quantities back into the rate-limiting step. Sixth, eliminate all unmeasurable quantities remaining by doing a total catalyst balance. Seventh, linearize the rate law to see if the data fits. Eighth, if the data does not form a line, then one or more assumptions must be incorrect. And finally, having physical knowledge of the chemicals and catalyst involved will give insight into what assumptions are likely to be correct. So what did we learn today? Kinetics describe how quickly reactions happen. The equation describing the kinetics of a reaction is known as the rate law. Rate laws must be determined from experimental data. Single-step reactions are usually rate laws. Multiple-step reactions have more complicated rate laws. Rate laws can be derived by a relatively simple procedure. The easiest way to see if a rate law is consistent with experimental data is by linearizing the rate law. And there are several ways to do this. Well, that's all we have for you guys today. Thank you so much for watching, and have a good one.